Imagine looking at a vast, featureless blank space. Suppose someone asks you to identify the exact location of a single black dot resting right here. How do you describe where it is? Without any reference points, it is impossible. The author Lewis Carroll famously questioned the necessity of the arbitrary lines we draw across the world. He wrote of his characters crying out, "What's the good of Mercator's North Poles and equators? They are merely conventional signs." But those conventional signs are precisely what mapmakers have relied on for centuries to navigate the globe safely. Today, we move from a basic classroom grid to the universal mathematical map. To follow along, you will need a piece of graph paper, a standard pencil, and a straight edge. Locating an object is never a matter of describing what it looks like. It requires establishing two independent distances from two fixed intersecting lines. Let's start with a physical example. Look at this structured classroom. The desks are arranged in a strict, predictable layout. To find a specific student's desk, you need two independent pieces of information. First, the column, counting from left to right. Second, the row, counting from bottom to top. If we need to find the student sitting in column 5 and row 3, we trace those paths until they cross. We write this combined location as the coordinate pair 5, 3. The order of those numbers dictates the location. If we reverse them to 3, 5, we are now looking at column 3, row 5, a completely different desk. In any mapping system, agreeing on the sequence of information ensures everyone ends up in the exact same spot. This logic was formalized by the 17th century philosopher René Descartes. He applied the geographic concept of latitude and longitude to a flat plane. When we transition from physical desks to a clean mathematical plane, we replace the terms column and row with two perpendicular lines, the horizontal x-axis and the vertical y-axis. The exact spot where these two axes intersect is called the origin. It acts as the absolute 0 point for all movement on the plane. The origin is the anchor of the entire system. By starting every measurement from this shared 0 point, multiple people can navigate the plane independently and still arrive at the exact same location. Let's look at the standard notation for plotting a location. We place the coordinates in brackets. The x-coordinate, representing the horizontal distance, always comes first. The y-coordinate, representing the vertical distance, always follows. To plot the point 4, 3, we start at the origin. First, we measure our perpendicular distance from the vertical y-axis by moving 4 units to the right along the horizontal x-axis. Next, we measure our perpendicular distance from the x-axis. From that spot, we move 3 units straight up, parallel to the y-axis, and mark our point, P. Think of it as having to run before you jump. You move horizontally along the x-axis first before moving vertically. Not every position exists in the positive direction. For points located to the left or below the origin, we use negative coordinates. The crossing axes divide the plane into 4 parts, called quadrants. We number them 1 through 4, moving counterclockwise. Each quadrant has a specific combination of positive and negative signs. Let's plot point Q at -6, -2. Starting at the 0 point, we move -6 units horizontally into the negative x-axis and -2 units vertically. This places point Q securely in the 3rd quadrant. With these 4 quadrants, we have a system that stretches endlessly in all directions. It turns a blank surface into a structured field of data. To recap, whenever you need to find a location, start at the origin, run along the horizontal x-axis, and jump along the vertical y-axis. Looking at this completed map, every single plotted point is now uniquely identifiable. Because the rules are uniform, these positions are entirely reproducible. Here is your final task. Grab your graph paper and plot 3 random dots. Write down their coordinates, hand that list to a friend, and see if they can map those exact same locations without looking at your paper. By mastering these conventional signs, you no longer have to guess where something is. You can define any position in a 2-dimensional world with absolute mathematical certainty.